Welcome to the skill video for skill number 82. I can solve radical equations and inequalities. This skill would be broken into two parts. First, we should be able to solve a radical equation, and on the second day we'll look at radical inequalities. I've outlined steps for solving radical equations below. First step, what I like to call step 0, is isolate radical. The reason I call it step 0 is a lot of times it's already isolated. Step 1, solve algebraically. Step 2, find constraints set by the radicand. Step 3 and 4, test the solution against the constraints and original equation. And then step 5 is to write the solution. I outline the steps in this fashion so that it connects more directly to the second part, which is solving inequalities. So the 5-step process will be more or less the same for inequalities. So let's take a look at our first example. Root x plus 7 plus 5 equals 8. So in step 0, we need to isolate the radical. So we do that by subtracting 5 from both sides. And in doing that, we get root x plus 7 equals 3. And then step 1, we solve algebraically. So the way I went about solving this algebraically was first I squared both sides. So if I square both sides, that gives me x plus 7 equals 9. And then I subtract 7 from both sides, getting x equals 2. A lot of people would be inclined to stop here, but we have to check to make sure the answer works. And I know this is annoying to have to check your work, but oftentimes in this sort of problem, we generate what's called an extraneous solution. So we need to make sure that it's not extraneous. So in step 2, we find the constraint set by the radicand. It's not possible to take the square root of a negative number, so our radicand has to be greater than or equal to 0. So we find that x is greater than or equal to negative 7. So far, that's good. That matches with our answer. So in step 3, we test solution against constraints and the original equation. So our solution is greater than negative 7, so it checks out against our constraints, and then we plug the solution into our original equation. So we get the root 2 plus 7, which is root 9 plus 5 equals 8, and that checks out. So 3 plus 5 is 8. So our solution then is x equals 2. I didn't write that in here. Step 5, x equals 2. Okay. And to reiterate, step 3 and 4 is important because sometimes we introduce extraneous solutions which must be removed from our solution set. And I'll show you that in example 2. All right, example 2 reads x is equal to the square root of quantity x plus 1 plus 5. So our initial step was to isolate the radical. So I did that by subtracting 5 from both sides, and I got x minus 5 equals root x plus 1. Then we go about solving it algebraically. And to get rid of the square root symbol, I took the square of both sides. If we square x minus 5 squared, we have x minus 5 times x minus 5, and we want to FOIL that. So x squared minus 5x minus 5x plus 25. And that's what we have here, x squared minus 10x plus 25. We notice it's a quadratic, so in the process of solving a quadratic, it's best to put it into standard form. So I subtracted x from both sides, and I subtracted 1 from both sides. And now that it's in standard form, I can try to factor it. And this particular example does factor. So it gives us the answers x equals 8 or x equals 3. And we would normally want to stop here, but we have to check against any constraints set on by the problem and check it against the original equation. So the first part of that is we find the constraint set by the radicand. X plus 1 has to be greater than or equal to 0. So anytime we have an even root, the radicand has to be positive. So square roots, fourth roots, sixth roots. X plus 1 is greater than or equal to 0, and that makes x has to be greater than or equal to -1. Step 3 and 4, we test the solution against the constraints and the original equation. So x equals 8 and x equals 3, both are greater than -1, so it checks out against our constraints. And then we check them against the original equation, which means we plug 8 into the original equation and 3. So if we plug in 8, we get 8 plus root 9, 8 equals root 9 plus 5. And that checks out. Then we try with the 3, and we get 3 equals root 3 plus 1 plus 5. And we find that that does not check out, because if we evaluate that, we get 3 equals root 4 plus 5, which means 3 is equal to 2 plus 5. And that is not true. So that is called an extraneous solution, and we find x equals 8 is our only solution. It's also possible to have two solutions where both of them are part of the solution and neither of them are extraneous. And I've done that in example 3 here. So the radical is already isolated. So in the first step, I was solving algebraically, so I squared both sides. I factored out I distributed the n minus 7 squared to get n squared minus 14n plus 49. In the next step, I subtracted 3n and added 21. I then factored my n squared minus 17n plus 70. And that gave me two possible solutions of n equals 7 or n equals 10. When I was checking the constraints of the domain, first I found the constraints of the domain. So I said that the radicand had to be positive, and that concluded that n had to be greater than or equal to 7. This checks out for both of my answers. So then I have to plug the answers into the original equation. So first I plugged 7 in for the n's, and I found that 0 equals the square root of 0, and that checks out. And then I did the same thing for 10. I plugged 10 into the original equation, and I found that 3 equals root 9, and that checked out. So both answers are part of the solution set. We could, if we wanted to, write it in roster notation, 7, 10, close brace. All right, when it comes to solving radical inequalities, which is the second part of the skill, the steps are very similar. Our initial step is to isolate the radical. Our first step is to solve the equation algebraically. Step 2 is to find the constraints set by the radicand. And then step 3 and 4 are written slightly differently, but it's still the same basic idea. Step 3, we graph on a number line to find the viable solution set. And that what you're doing there is you're testing your solution against the constraints of the radicand. And then step 4, we're testing the solution against the original inequality. So in step 3, you're actually creating your solution set, whereas previously we had created that in step 1, but now we don't get it until step 3. And then you use that solution set that you find, this solution set you use in step 4. And if it checks out, then you write it as your solution in step 5. I've added a step 6 here that says use a graph to verify the results, because on the worksheet that I do with this skill, we practice our graphing. So let's see how that plays out with an example. Okay. What we have here is the negative square root of x minus 3 plus 4 is greater than 2. So in step 0, we want to isolate the radical. So the first thing I did was I subtracted 4 from both sides, and then I divided both sides by a negative. And remember, when you divide both sides by negative, the inequality is going to turn directions. Step 1, we solve algebraically. So I squared both sides, giving me x minus 3 is less than 4. And then I added 3 to both sides to give me x is less than 7. In step 2, I find the constraint set by the radicand. So I found that x minus 3 has to be greater than 0, greater than or equal to 0. It must be positive, which means x is greater than or equal to 3. In step 3, I graph on number line to find viable solution set. So first I graph the x is less than 7, so an open circle on 7, and x is less than it, so we go to the left. And then x is greater than or equal to 3, so a closed circle on 3 and a line to the right, which means our solution appears to be the area where both of these lines are true, and that's only between 3 and 7. So both of those lines are true between 3 and 7, including 3, excluding 7. So right now it appears our solution to be 3 is less than or equal to x is less than 7. So we want to check that against our original equation. So I pick a number in that set, and I'm going to pick the number 4, and I plug 4 into the original equation, and it checks out. So I now know that that is the solution set. We have to do this step because it does not always check out. Step 5, we write the solution set. I wrote it in set builder notation. That's pretty common for inequality problems, to write the solution set as a set builder notation. And then step 6, we draw the graph of it, just to check by a graph. So what I did is first I graphed the 2 as a dashed line. Here, I'll zoom in on this. So I graphed the 2 as a number line, horizontal line that's dashed because it's less than 2. And then I graphed the equation. And the equation had a shift to the right of 3 units. So 1, 2, 3. And then a shift up 4 units. 1, 2, 3, 4. So there's the start point. And then it was also reflected. So I'm going to go down 1 to the right 1, down 1 to the right 3, down 1 to the right 5, etc. And now I want to find when is my curve greater than 2. And my curve is greater than 2 from here to here. We include the start point of 3, but where it crosses at 7, we do not include because it's a dashed line. All right, the key ideas and concepts for this lesson: we should be able to solve a radical equation, something to the effect of this. Would probably be about as complex as it will get. It should be noted, it's not always a square root. Sometimes it's going to be a third root or a fourth root. And in doing this, we have to remember that we have to set constraints on the radicand. So if it's an even root, like this square root, then our radicand has to be greater than or equal to 0. If it's an odd root, there are no constraints set by the radicand. And then we also have to check against our check against our original equation. And I know that this is to many an unnecessary step, but we got to do it. And finally, we should also be able to do this with inequalities. The process is fairly similar. The solution set is slightly different.